Log on, tune in, find out. Another good idea from Cambridge.
On Hodge polynomials of modular spaces of SL2 character varieties.
Thank you. Let me thank first the organizers for giving me the opportunity of talking here in this great room. So we are going to talk about these Hodge polynomials of SL2 C character varieties. Do you hear me well, or I mean, if there is anything, please tell me. So first, let me explain you what I understand as a SL2C character variety. So we start with a finitely presented group finite set of relations. And for us, a SL2C character variety is just the space the conjugated orbits of representations of this finitely presented group. It happens that when gamma is chosen to be the fundamental group of a Riemann surface, compact Riemann surface, and P is a point in the surface, then this Moduli space, this space of representations, is known to be diffeomorphic to a Moduli space of Higgs-Mandels with, in this case, degree 1, rank 2, and fixed determinant. This is due to the so-called non-abelian Hodge theorem, due to the efforts of several people that are Corlett, Donaldson, Hitchin, and Simpson. It is known that these two varieties are hyperkähler, but they are the algebraic structure is completely different. One of them is just an affine space, while the Moduli space of Higgs-Mandels, we have heard it several times during the last weeks, is a fibration by Lagrangian subvarieties. So it makes sense to study some geometric structures on these Moduli spaces and then compare them. For instance, to study the mixed Hodge structures. So this, the last years, the following people, Andrea Cataldo, Thomas Hausel, Luca Migliorini, and Fernando Rodriguez Villegas have compared the mixed Hodge structures on both sides of the quality, and actually Merev gave the Hodge polynomial for this thing last summer. Yeah. So for any genus but rank 2. So what are we going to do then? I mean, our goal will be to do the following. Well, first of all, let me say the Merev compute these Hodge polynomials using counting polynomials. I mean, using conjecture by cat, well, the work by cat, he computes these Hodge polynomials. So our goal will be to consider the following presented group. I'm not cheating. This is almost the same. We choose this following set of relations. We don't restrict ourselves to fixing the holonomy to be one like is in there. We fix the holonomy to be the identity, to be -1. Sorry, there is a -1. To be this of Jordan form. Matrices and this diagonal matrix. So let me say that let me just denote by it when we fix it to be the identity, so it corresponds to moduli spaces of Higgs bundles of degree 0. M minus it is the previous one. This Higgs bundles degree 1, of course rank 2. These are semi-stable, of course. And fix determinant. For the positive Jordan 4, we denote it by J plus. We don't know which space. And J minus to the other Jordan form. And let me just mention that the other diagonal matrices correspond to moduli space of parabolic Higgs bundles. So there is a non-abelian Hodge theorem for non-compact Riemann surfaces, and then the corresponding notion is the notion of a parabolic Higgs bundle. So this is our goal, and let me just define the elements involved. That is, we are going to study mixed Hodge structures, Hodge polynomials, and so let me just recall what are they. So pure Hodge structure of weight K is just a finite dimensional complex vector space provided with a real structure such it has a decomposition satisfying that for complex conjugation with respect to the real structure, it was like this. So this gives us the so-called Hodge filtration, which is a descending filtration defined as the following: the sum of the pieces of the filtration, and of course it corresponds just to the quotient of two of these pieces. So then a mixed Hodge structure is again a complex vector space, finite dimensional, with a real structure, such that it has an ascending filtration, called weight filtration, together with descending filtration, with the property of inducing a Hodge structure of weight k in the pieces of the filtration, of the ascending filtration. In the k pieces of the ascending filtration. So, with these notions, let me recall you that the link prove that for set a quasi-projective variety, then its cohomology and the cohomology with compact support are provided with mixed Hodge structures. Moreover, if set is smooth and connected and compact, then they are pure Hodge structures. So then we call the Hodge numbers to the dimension of the pieces of the mixed Hodge structure, and define the Euler characteristic. Well, for the compact homology will be the same. Actually, we are using compact homology, so the Euler characteristic is defined as the sum over all case of these Hodge numbers, and then finally our Hodge polynomial is the following sum. Well, as you can imagine, computing Hodge polynomials could be sometimes difficult, especially for these big moduli spaces. But what we are going to do is to show a way to prove, to compute it in an easy way, just dividing them by pieces divided the spaces by pieces. So by pieces such that the Hodge polynomials work well with them. So we are going to prove some key properties of these mixed Hodge structures. And then we will use them to compute the Hodge polynomials of all of these varieties. So let me start easy. And well, first, if you have an algebraic variety over C, it works also with any field, any closed field, algebraically closed field. Then this set is the union of locally closed subvarieties. Then the Hodge polynomial is the sum of the Hodge polynomials of the subvarieties. For this is just to prove this is just enough to see that for the long exact sequence in cohomology, the filtrations are just compatible with these arrows. So then the Euler characteristic is deduced from this. Also, just for the properties, from the cohomology of Cn, we can compute just the Hodge polynomial of Cn. Again, for Pn is just sorry. Let me say here that when we have that the Hodge numbers are 0 for P different than Q, we will call it, we are thinking that maybe it's not the best way to call it, we call them varieties of pure type. Please don't confuse with pure Hodge structure. And then for convenience, we use U times V, just being Q. So that's that. So the Hodge polynomial for Pn is okay. Is this one, and from first ones you can just think that from 1 and 2 you can deduce that the polynomial of Cn minus 1 point, then it is Qn minus 1, and so on. But there are some better tricks that we are going to use. Actually, let me show you a proposition which contains some tricks. And it's the following. So we have P connected and an algebraic fiber bundle with fibers denoted by F. Suppose that the action of the base on the compact homology of the fibers is trivial, then the Hodge polynomial of the total space is the Hodge polynomial of the fiber times the Hodge polynomial of the base. How to prove this is just consider the Leray spectral sequence for pi, and then see that the E2 term is just the tensor product, and it aboutes to the cohomology of the total space. So then, as the Leray spectral sequence respects the mixed Hodge structure, then we have the result. And let me just point that in particular this proposition holds for the following particular cases. If we have B irreducible and pi a locally trivial fibration in Zariski topology, then the Hodge polynomial is the product of the Hodge polynomials again. For that, you use that is locally trivial, I mean, in Zariski topology, and then show that that using the Van Kampen theorem, that then the action, the monodromy action on the fibers is trivial too. Then another situation is when we have amorphins between quasi-projective varieties, where the fibers are projective spaces. Then in this situation, it's also the product of the Hodge polynomial of Z will be the Hodge polynomial of the product. And finally, the case of principal Givander, because using that if it is if the group structure group is connected, well, then we have also a trivial action of the monodromy. Well, the last trick is, let me write it here because we are going to use it several times, is we will need the Hodge polynomial for something where we have a Z2 action. So in this situation, we denote with plus minus for the cohomology, the plus minus invariant part of the cohomology. And then, of course, as it is a finite group and is C2, then EZ plus is the Hodge polynomial of this quotient, and is Z minus is just the rest. Let me show you, just to not get bored. For instance, if we have a G star with a sec to action like this, then the Hodge polynomial of will be just Q, because this is just C, and then C, sorry, this will be here, observe that then this is minus 1, since Z is Q minus 1. This is a funny thing, we have these negative Hodge polynomials because we are dealing with mixed Hodge structures. So let me put here another important proposition for us, that is the following. So if we have the following diagram of vibrations, where B, where this one is a locally trivial derivation, P and P tilde are smooth, well, this is a locally trivial expression in the usual topology. And also the monodromy action, the monodromy action is trivial. Then the Hodge polynomial is then the following sum. So the ingredients of the proof for this proposition are just that as this action is trivial, it factors through an action of Z2 on this cohomology, splitting this in the plus invariant part and the minus invariant part, and then taking the E2 terms for this Delaunay spectral sequence for P tilde and P, then and comparing them, we get the sum. So finally, with respect to this pure type, just let me tell you. The following. If we have Y and the bike variety, yes, which is a disjoint union of a closed variety and the remaining one, then if two of the free spaces set Y U are of pure type, so then so is the third. Second, yes, if we have this algebraic fiber bundle with monodromy axiom trivial, then if B and F are of pure type, so then so is set. And third, again, for the situation of an action of C2, if set is pure type, then so is the quotient. So this implies that in our situation, all our pieces will be of pure type. Okay, so then I start with some warming up examples. And let's do some easy computations. What is the Hodge polynomial of GL to C? Well, it's easy to compute using our tricks. So just consider the following locally trivial figuration. Just take these matrices into A and B. So then the Hodge polynomial will be Hodge polynomial of the base times the Hodge polynomial of the fibers, which was easy to compute because we know what it is. So, okay, we just want to have it. Now, what is the Hodge polynomial DL to C? Well, the natural figuration that we will think of is this one, but this is not locally trivial, but it's like a bundle, a G bundle with a. Sorry? Sorry. Yeah. But as we have that, I mean, it's we apply we are we have a trivial monodromy action of the base on the fibers. So then this is just okay. We have the other one minus this, so it's divided by this, so it's this one. Another way to see this is to check that this is like having P3 minus P1 by P1, and then you have the same. And finally, the Hodge polynomial of SL to C is It's the same as above. And we compute it the following way. We have a locally trivial cube vibration in Zariski top, which is the following. So then it's q2 minus 1 times q. So then this is the Hodge polynomial. Well, so our goal is to provide with a method to compute Hodge polynomials for character varieties. So let us see here. What we are going to use is just orbit spaces that we will be after use for dividing the SL2 C group into pieces that are nice for us. So I mean, we use the L to C action on SL2 to divide it into the following orbits. I mean by this the orbit space corresponding to the identity, the minus identity, this Jordan matrix, and of course the union of this space, that is Gen union, and it gave us SL2C. So then we can compute the Hodge polynomials of these orbits, and just as a hint that it is also not as easy as there, but also easy, as this is diagonal, it commutes with all GL2, so this is just a single point. So it is a 1. For these matrices, the stabilizer is C star by C. So we just have to compute the Hodge polynomial of this. So it gave us this thing, and this one is a bit more involved. Let me just write here. For that, we see that the stabilizer of these matrices is the diagonal matrices, so we have kind of diagram like that one. And also we can interchange these lambdas, so we have an action of set 2 on these orbits. So the ones we are interested on are these ones. So this denotes matrices lambda and P, where P belongs to GL2 quotient by the diagonal matrices, and we send it to C minus 0 plus minus 1. We just sum this, and so we go to C times minus plus minus 2, and here we use the trace. So then the Hodge polynomial of this is the Hodge polynomial of the fiber, the plus invariant part times the base, also the plus invariant part, and so on. So it gives us let me write you who are them. So we just have okay, so if we add them, we have 2 here, 2 times this q minus 1 plus this q2 minus 1. So the sum of all of this should give us q3 minus q, and it is okay. 2 times this, we have the q3 minus q, and this 2 times goes with this 2 times, so then it is okay. So we already checked that then stratifying SL2C works and give us the right Hodge polynomial. This is a hope. So then let's use the trick with our stuff. So the main idea is to use the commutator map so consider this map. And then to the commutator of the 2 matrices. Of course, the inverses of that orbit sorry. The union of these orbits give us SL2C to the square, but also they give us these things, which with the appropriate quotient give us our model spaces. So this is the main trick. Also, watch the following. This union is this union gives us the whole SL2C. So it also gives us a way to prove and to test if our polynomials for each of the spaces are okay. Well, if we do well the quotient. So results. Okay, we don't need more. This one. We don't remember it. So writing here for all these matrices, we no, not this. Our spaces. So then first I start with M for the identity. So this character variety contains reducibles. When we mean by reducibles that there is one eigenspace common to all the matrices involved in the equation. So what we have to do is a GAT quotient. So we identify the S-equivalence classes, and so the non-diagonal classes have a limit in the diagonal classes. So each S-equivalence class contains an element of the form AB equal to this, which is unique up to acid to axiom. That interchange the eigenvalues. So okay, it's like we have diagram of iterations as before, where the base is, of course, these lambdas and mu's has to be different than 0. So our Hodge polynomial for our MD, which is this one, is just the as before, using our relations and using the formula in the proposition is this one. Now we are going to compare it with the one for the Higgs moduli space. So Okay. Let me. Okay, this is here. Just before comparing with the Higgs modular space, let me just give you the one for the twisted character variety. This is also known as twisted character variety because of how Schell called it's that way. So in this situation, this is isomorphic. We can just see that by computation. Isomorphic to PGL2C. So then, obviously, the Hodge polynomial is -1. And sorry, 1. I mean, it's a polynomial of a single point. So it's 1. And another interesting one, because it was related with the parabolic Higgs bundles, is the m lambda. Just let me write you up what it is. So I have, I think, 2 minutes. Okay. And before going to the thing that you are more interested on, let me just make the advertisement, which is also interesting. Okay, the information that we have is not enough to compute the Poincare polynomials. I mean, if the variety is smooth, then the Hodge polynomials and are related with the Poincare polynomials in this way. But if just because we are having pure Hodge structure, but in this situation we can have cancellation. So then we need more information to compute the Poincare polynomial from our Hodge numbers. So, for instance, for MB, we have an explicit description of this variety as C star by C star quotient by C2, as we write down, I don't know where, there. So then the Hodge numbers are these ones, and please notice that they are purely mixed, because I mean, for instance, the sum of the P and Q is not exactly K, so these are not pure Hodge structures. So then for C cross C we have and let me just we can basically And the action of the set 2 action on the cohomology has as a plus invariant part H2 and H4 and minus H3. So the non-zero numbers, Hodge numbers, are then and as I say with C star, with the Moduli, with the character variety for the identity, this is exactly purely, I mean, it's truly mixed Hodge structure. So, well, the Poincare polynomial is then I use here the Poincare duality for the Hodge numbers. So let's now compare with the Higgs situation. Well, in this case, the model space of Higgs bundles is the model space of Higgs bundles over an elliptic curve, and this has a explicit description as the following. Just take the curve. The Higgs bundle we are thinking of is just some flat bundles over the Riemann surface. We have Higgs field like this, and then so the space of holomorphic one forms is one-dimensional. So this is our C, complex numbers, and these are the line bundles over X, which are parameterized by the Jacobian, which is isomorphic to C itself. And we also have a C star action that gives changing the line bundles and changing the values of, I mean, the one forms here. So then this Hodge polynomial can be computed explicitly, and it is the Hodge numbers for this are one, and when we use the C2 action on C times the curve, then it acts on H4 and H2 with the plus part, and on H3 with the minus. So then the Hodge numbers for M Higgs are the ones that are non-zero are these ones. That's equal to 1. So then our Hodge polynomial is q to the square plus q, which is different than the Hodge polynomial that we have for the identity. Also here we see that the sum p plus q is giving us as k. So I mean, this is obvious that then it's a pure Hodge structure, while in the other situation we have a mixed Hodge structure. So then our hope is to consider this map and then with the computations of the previous Hodge polynomials be able to compute the whole character varieties for any genus and also any kind of relation, I mean, even with the non-diagonal matrices. That's it.
Any questions?
So is the technique the same for high G?
Yeah, well, using, I mean, with this, can you, for instance, we will map and then have identity minus identity and so on. So use the stratification and cut it in a nice way and have it. Hopefully the stratifications are nice enough to be just plugged for the next ones. I mean, and have a kind of recursion. But I mean, this is an ongoing problem.
Any more questions? In that case, can we thank the speakers?